We said in the big picture video, this unit is a battle of terminology and relationships. If you can keep your terminology straight, it is easy to figure out the relationships between your compounds when you are asked to do so on a test. You are tested on these like crazy. So the way that I approach this is off the bat, before you even start anything stereochem related, I want to introduce to you what I call the flowchart. The flowchart is incredibly important. This is going to be your system of how you keep all the terminology straight. So we are going to give you a shortened version of it today, and we are going to expand on it in later videos in massive, massive detail. But what I want to talk about at this juncture in the class, your professor is going to start talking about isomers. And isomers, they'll start throwing terms out. Constitutional isomers, stereoisomers. Let's break down what isomers are first and foremost. So the first piece of terminology that you need in this unit is that isomers are compounds that have the same molecular formula, but are different for some reason. And we're going to specify why. Now, at this juncture in the class, there are going to be two types of isomers that you are responsible for. There are what we call constitutional isomers, and what we're working towards here, which are stereoisomers. So before we even get into stereoisomers, let's define the two different types of isomers. So constitutional isomers are going to have the same formula, but they are going to have different connections. That is how you are going to be able to tell if you have a constitutional isomer. So take my word for it at this moment in time. You could check me on this if you wanted to, but both of these compounds here have the formula C4H10. So what you'd notice here is since these have the exact same formula, but are connected differently, they would be constitutional isomers. Another way that you can tell that things are constitutional isomers is if you apply the nomenclature rules that you know, constitutional isomers are going to be named differently. They will never fail that test. So this would be 2-methylpropane, and this would be butane here. That's one way that you can tell. If there's an example that needs some extra attention or something seems off. Now, next up, stereoisomers. Stereoisomers have the same formula. They have the same connections, but what they have are different arrangements in 3D space. Okay, usually that is expressed through wedges and dashes. Not always, but usually. So I'm just going to put that there. Okay, so these two compounds here that I'm about to draw, these have the same, oops, I'm going to draw it over here. These two compounds have the same chemical formula. They have the same connections. They both have an OH group happening off of carbon 2, but different 3D arrangements. So the thing that separates constitutional isomers and stereoisomers, I'm just going to drive this home, is having the same connections or different connections. So that's what you want to be on the lookout for. The flowchart is set up for you to ask questions, and I'll show you how to ask questions with the flowchart. And of course, we have different types of stereoisomers coming. This is where the terminology really ratchets up. That's coming soon in later videos. We got to build our way up there. So let's try it out, okay? I'm going to ask you, what is the relationship between the following molecules? Are these constitutional isomers, stereoisomers, or completely different? So I'm going to help you out with this first one here. because I want you to see what's going on. The flowchart is designed for you to ask questions. So first off, if you are trying to figure out relationships, you're going to ask, do I have isomers? So these are compounds that have the same molecular formula, but are different. If you calculated and counted the molecular formulas for these two compounds, this one over here has C6H14. I highly recommend that you check me on that, okay? The one over on the right has the formula C6H12. This is how professors will be extraordinarily sneaky. So with the flowchart, we want to first check if our compounds have the same molecular formula. Well, unfortunately, these two compounds do not have the same molecular formula. So they are not isomers, and they don't fall anywhere on the flowchart. This is a trick problem. I put this here on purpose. These two compounds are completely different. They are not isomers. I'm going to show you one more, and then I'm going to have you do the rest. So let's take a look at number 2. Here, what I want you to notice is if we counted everything, these have the same molecular formula, okay? They both have four carbons. They should have 10 hydrogens and 2 oxygens. There. So with that, then we are going to ask, do these compounds have different connections, or do they have the same connections? If they have different connections, they're automatically constitutional isomers. If they have the same connections, they are stereoisomers. So with both of these, they both have a 4-carbon chain, and OH is coming off of carbons 2 and 3. So these have the same chemical formula, the same connections, but different 3D arrangements in space with those wedges and dashes. These would be stereoisomers. So keeping that info in mind, all I'm going to have you do at the outset here is pause your video, figure out the relationships for the remaining 4, and we'll check back in a second. All right, this next one, what I hope you saw is that we have different chemical formulas. So since we have different chemical formulas, different atoms, these aren't isomers at all. These are just completely different compounds, and we are done. This next one is purposely tricky. And this is something that professors will do. So first off, what I want you to notice, we have the same chemical formula. 6 carbons, 12 hydrogens, 2 fluorines for both of these. Or 10 hydrogens, 2 fluorines for both of these. Now, with that being said, we are going to ask if these have the same connections or different connections. And what I want you to notice here is in this first example, our fluorines happen at carbons 1 and 2. In this example, our fluorines happen at carbons 1 and 3. So these wedges and dashes were just there to throw you off. These have different connections, so they automatically fall into our constitutional isomer category. Next up, what I want you to see here is if we figure out the chemical formula for both of these both have the chemical formula C6H14, so they are isomers. Then we are going to ask if they have the same or different connections. They have different connections because here we have a 4-carbon chain with methyl groups coming off of carbons 1, 2, and 3. Here our methyl groups are both coming off of carbon 2. Different connections, constitutional isomers. Last one, we have 2 compounds with the same formula. they have the same connections in both. Fluorine is coming off of carbon 2. They have different 3D arrangements in space, so therefore these are stereoisomers. That's what's going on. It's all a matter of figuring out definitions, and you have made progress towards that. I want you to be very, very clear about these definitions, because in the videos to follow, a couple videos down the line, we are going to start adding in that really intense terminology that your professor is going to go over. If you've already gone over it, they're called enantiomers and diastereomers, and then you add meso compounds in on top of it. So we want to get you very clear. This is the first step of that. We are going to leave the flowchart for the next few videos, teach you some really tedious skills that will allow us to complete the flowchart and bring all your knowledge together. I'll see you in the next one.